Today we're going to be talking about my HPLC Analytical Lab project. To start off, we're going to be talking about our sample. In this case, our sample is a liquid sample, hence the name HPLC. This liquid sample is incredibly dilute, and we only need a few hundred microliters. From that few hundred microliters, our injector also uses an autosampler needle to take up between 50 to 100 microliters of that sample and then put it to our ejection port to go onto our column. Moving on from our sample, we have our mobile phase, which is our solvent system. In this case, we use something known as gradient elution. We mix multiple solvents of slightly different polarities to help alter the mobile phase on our column during the experiment. So what's important to note is that all of these solvents have to be miscible. So a good example of that would be something like water, ethanol, and acetone for a reverse phase HPLC experiment. And so this is all very useful in helping to separate out our peaks later on. Moving on, we have our pump, which helps to push our solvent system through the column. In this case, we're using a piston-based pump. It supplies a constant high pressure, roughly somewhere between 300 to 400 bar. And this high pressure helps to increase the resolution as well. Moving on from our pump, we have our column, which is our stationary phase. We have it's most common to have a very packed stationary phase in a small area because this increases the analyte's ability to interact with the stationary phase during the experiment. It's also important to note that it's incredibly packed because it's such a short column. It's roughly somewhere between 10 to 25 centimeters usually, and the packed allows for more interactions to occur. We're able to control the polarity of our stationary phase on our column by changing what material is inside of that column. The most common one for reverse phase HPLC is C18. It's a very long hydrocarbon chain, very hydrophobic. If we wanted to run a normal HPLC phase experiment, we would use a very polar material as our stationary phase. Moving on from our stationary phase, we have our detector system. In HPLC, there are two main types of detectors. The first one I'm going to be talking about is UV-Vis. UV-Vis is commonly found with standalone HPLC systems. The UV-Vis measures the absorbance as the sample passes through the detector, and it works very well with compounds that are absorbed in that UV-Vis region. So it gives us both quantitative and qualitative results. Qualitatively, we're able to compare results from multiple different experiments so long as we keep the wavelength set at a very specific value. And then quantitatively, we have something called Beer's law, which allows us to compare concentration values as well. The issues with this is not everything absorbs in the same range. And so if something's absorbed outside of the UV-Vis region, it can't even be detected, and so that can cause issues in our experiment. Also, since we're working at such low concentrations, it could be so low that we don't even notice an absorption, unless you were to increase that concentration. So the other type of detector system we have is an MSMS. This is a tandem mass spec, and so a tandem mass spec helps with fragmentation. So in this case, it allows us to isolate out a single parent ion and then view how that fragments. And this is relevant specifically when you're looking at something like electrospray ionization. Electrospray ionization is a very soft method of fragmentation. It allows us to put a potential difference across an area, and so as our solvent droplets pass through that area, charges will surround solvent droplets, and as the solvent evaporates, the charges are able to softly break apart the analytes. The issue with this is that the mass to charge ratio, the charge is not always 1, so that's why we use the tandem mass spec to separate out that single parent ion and view the fragments where the charge is only 1. This also gives us super high resolution, but the issue with tandem mass specs is that they're expensive and the maintenance required is very complicated. A good example of this is the turbomolecular pump. It's not cheap at all, and it takes a lot of time to fix any issues with it. One other form of ionization that the MSMS uses is atmospheric pressure chemical ionization. Instead of placing that potential difference across the entire detector, what it does is it places that potential difference across the needle, and when the solvent leaves the needle, it causes something known as corona discharge. This discharge attracts water ions to the solvent, specifically H3O+. These H3O+ ions absorb the solvent to them, and the H3O+ becomes H2O, leaving behind that proton. That proton then is able to fragment our analyte, and then the fragments are drawn towards the detector slit. Finally, we have our computer, which is able to tell us what the results of our experiment was. And so what we have here is just a simple mass spec result.